Howdy, today on Flippin Science we're looking at energy profile diagrams. So science understanding we're going to look at, energy profile diagrams can be used to represent relative enthalpies of reactants and products, activation energy and enthalpy change. Draw and interpret energy profile diagrams. So let's start by looking at endothermic and exothermic reactions. Reactions that release energy into the environment are called exothermic reactions, and reactions that absorb energy from the environment are called endothermic reactions. A good example of an endothermic reaction is photosynthesis. So down here we have some green leaves, they're absorbing light energy, and they use that light energy to make glucose and oxygen from carbon dioxide and water. So it's endothermic because it's absorbing light energy from the environment in order for the reaction to occur. Here we have these sneakers burning. You can see heat and light coming out from the sneakers. The combustion of the sneaker is an exothermic reaction. That energy being released is the heat and light that you see there. So here we have an endothermic reaction over here in this video. And as always, thanks to Resource for these videos. Here we're dissolving a salt in water. Now this is a physical change, it's not a chemical change. We can see the temperature of the water is decreasing. And the reason for that is energy is required from the water in order to break the salt up into its ions, in this case potassium chloride. So that is absorbing energy from the water in order to do that, and we see that as a temperature change. Over here we have an exothermic reaction. So we're going to put some magnesium in hydrochloric acid solution. We can see it's already exothermic because we're getting steam being produced, vapor being produced, so it indicates that it's probably quite warm. We can see the temperature of the hydrochloric acid solution is also increasing here. So this is an exothermic reaction. Heat energy is being released into the environment, in this case the solution, but also into the atmosphere around it. So let's look at energy profile diagrams. An energy profile diagram shows the energy change in a reaction. You have energy of reactants, so if we look at our example down here, we've got nitrogen dioxide and carbon monoxide. These are our reactants. Their energy is represented on the left-hand side. We then have a change in energy, so that's this little hump here, and then we have our energy of our products on the right-hand side. In this case, our products are nitric oxide and carbon dioxide. I'm going to ask you a question: is this reaction endothermic or exothermic? So this reaction is exothermic, and we can tell that because energy is being released here. Our reactants have more energy than our products, so there's a difference there. So if there's a difference between the reactants and products, in this case, the reactants have more energy than the products, that means it's exothermic. Energy is being kicked out to the outside world. So we just saw in that example that exothermic reactions release energy into the environment. So the products of the energy of the products is less than the energy of the reactants. And we can use the word enthalpy here as well. We'll talk about that a bit later on. So here we have our exothermic reaction. The reactants have higher energy than the products do, and that difference in energy, that's being released into the environment. Endothermic reactions are different. So here we can see the energy of the products is greater than the energy of the reactants, and that difference of energy is the energy required to be absorbed by the reaction in order for the products to be produced from those reactants. So let's talk about the activation energy. The activation energy is the energy required for a reaction to take place. So we've kind of already talked about this a little bit before. It's sometimes given the symbol capital E subscript A. The activation energy is the energy required to break bonds in your reactants to produce what we call an activated complex. So we can see in both diagrams here we have an activated complex. This is an unstable arrangement of the reactants where the bonds are being broken in the reactants and they're ready to start producing products. Once the products start forming, so bonds form making the products, you get more stable products being produced, and they have a lower energy than the activated complex that you started with. And this happens in both endothermic and exothermic reactions. Here we can see the activation energy in the endothermic reaction. So it's the energy between the reactants and that activated complex. And then we get the energy returning back down to the products. Here it is in the exothermic reaction. And again, we have the energy of the reactants, the reaction of the products. The activation energy is this energy required to go from the reactants up to the activated complex and then back down. So we've talked about activation energy in terms of catalysts and enzymes previously. The activation energy can be reduced by using a catalyst or enzyme. We're talking about catalysts and enzymes that speed up reactions. The way they do this is they provide an alternate energy pathway of lower activation energy, so you don't need as much energy for the reaction to occur. The way this is shown on an energy profile diagram is the activation energy is smaller when you have a catalyst or an enzyme being used. So here we have the activation energy without the catalyst, and here we have it with the catalyst. We can see it's a bit lower here. This diagram over here shows the pathway in a little bit more detail. This is more detail than you would show, so don't do this in a test or an exam. But there can be multiple small steps happening with catalysts that each require a total of less energy than the presence of no catalyst at all. So that's why we mean by a pathway sometimes. It can be a series of reactions using a catalyst that reduce the energy required for the reaction to occur. So let's have a look at an example of reaction with a catalyst. Down here we have a solution of hydrogen peroxide, and in there's some detergent to capture the bubbles. This is reacting, but it's reacting very slowly. The hydrogen peroxide is turning into water and oxygen. Now this reaction happens at room temperature. Light can kick off this reaction as well, so a little bit of energy from light can make this reaction occur as well. We're going to add a catalyst. We're going to add potassium iodide catalyst. It's in solution. And let's see what happens. So here comes the potassium iodide solution, and we get the reaction happening quite quickly. This is called an elephant's toothpaste reaction. So what's happening here is, by adding the catalyst, the activation energy for the reaction to occur reduces. So that increases the rate of reaction. So we get lots and lots of oxygen being produced. And that oxygen is trapped in the detergent, so we get all these bubbles. So now let's talk about the enthalpy change. So the reactants and the products each have their total amount of energy, and we can call that an enthalpy. So enthalpy of reactants and enthalpy of products. The difference in energy between your reactants and products, we call that an enthalpy change, and that's referred to as delta H. So our symbol for that is delta H. Delta, used in science or maths, is a change in. So this is the change in enthalpy, and the symbol for enthalpy is H over here. Now it's important to note that when it comes to using catalysts, the energy of the reactants or products doesn't change. The only thing that changes is the activation energy. So that means that delta H isn't affected by catalysts or enzymes. The energy of the reactants and products doesn't change. The activation energy changes, but not the difference between them. So if we look at endothermic and exothermic reactions, we can get an idea of one aspect of delta H, which is sign, so whether it's positive or negative. In an exothermic reaction, the change in enthalpy is negative because we're going from high energy in the reactants down to low energy in the products. So this gives it delta H a negative sign. If we look at the endothermic reactions, we can see the difference between the reactants and the products. It's positive. We're going up. The products have more energy than the reactants. So the delta H value there is going to be positive. This is very important. It's very easy to get these mixed up, and these will be important later on. So here's a question. The energy change that occurs as a result of another reaction in the catalytic converter is shown in the diagram below. Identify which of P, Q, R, and S represents the enthalpy change. So the enthalpy change is going to be Q, because that's our difference between the reactants and the products. So that's our delta H value. So out of P, Q, R, and S, which one's the activation energy? The activation energy is going to be P. So that's the difference in energy between the reactants and then our activated complex at the top here. On the diagram above, it says draw a reaction pathway for this reaction in the absence of a catalyst. So we don't have a catalyst, so that means that the activation energy is going to be much higher. So my activation energy is going to be higher because we're talking about a catalytic converter. In a catalytic converter, there's catalyst presence. So without the catalytic converter, without the catalyst in the catalytic converter, the activation energy is going to be much higher. So the last part of the question asks, say and explain how the presence of the catalyst affects this reaction. So the catalyst increases the rate of reaction, and it does that by providing an alternate energy pathway of lower activation energy. That means that when the reactants collide, more particles have the activation energy required for the reaction to occur. And that leads to more successful collisions per unit time, which increases the rate of the reaction. So today on Flipping Science, we looked at interpreting energy profile diagrams. That's it for Flipping Science today. See ya.